So we're going to try a couple examples for goodness of fit tests as well as a comparison of two samples using a chi-square test. So here is a worksheet that is linked right here, and we'll pause if you want to download this and work with it. Come back and check your answers. So let's just try out two of these. A biology professor reports that historically grades in her introductory biology course have been distributed as follows: A's, B's, C's, D's, and F's. Grades in her most frequent course were distributed as follows. So the first thing that we want to be able to do is write our null hypothesis. And so when we look at this and we go, okay, what are we trying to measure here? So our null, if I select a pen, our null hypothesis would be the most recent grade distribution matches the historical grade distribution. With our alternative meaning this class is not like the historical grade distribution. So the most recent grade distribution differs. So that's our first part with this read. Next part, it says calculate the expected frequencies. So we could, knowing that the total population is 325, zoom in a little bit, for A would be 325 times the percentage. And we could go down the line for each one of these, or if we jump to our calculator, I've done a little bit of work ahead of us. I've got the grades, I've got our totals, and our percents. So I'm just going to type in our new column name and call it expected. And in the equation line, if I hit equals, I'll take my 325 and we'll multiply that by the percent column. And that's another way of getting the exact same values. So our expected A's would be 48.75, 97.5 for B's, 130 for C's, 32.5 for D's, and 16.25 for a grand total of, again, 325. As we go along with our chi-squared test of goodness of fit, we need to check the assumptions and conditions. So the ones that we need to check are counted data condition. Are our data counts? And we can see that all of these are counts. Next, we look at the randomization condition. And we can see that from the randomization condition, this is more of a convenient sample of students as opposed to a simple random sample. So what we're looking for is this class representative? So it would be safe to assume that this class is representative, and there's no reason to suspect bias. And lastly, our expected cell frequency condition. That's for both the counts and the totals, and none of them are below 5, so we're good. Now, just before we move on, I want to look at the histogram distributions. I wanted to show you guys, if we go to add data and statistics, we can go to look at the grades. And before, what we were doing is if we hit menu, and then you go to plot properties, and then you go to add a Y summary list, we can look at our totals for our grades and see our distribution. If we want to see how that compares to the expected values, it would be nice to be able to compare each column to the grades that we expect. And you can do that if you go to menu, plot properties, and then we're going to add a Y summary list. This time we're going to add the expected column. So we have our totals that we have right here compared to our expected column. And we can see that our blue distribution is slightly different than our orange distribution of what we expect. And what we want to be able to do with a goodness of fit is see, does our actual data match our theoretical distribution? So what we would need to do is calculate the degrees of freedom. With the degrees of freedom, that's one less than the number of categories. So there's 5 grades, so our degrees of freedom is 4. We could compute the components and find our chi-squared statistic. Again, to calculate components, it's observed minus the expected squared all over the expected value. And this is the nice thing about jumping to the calculator. Once we have all of that data, if I hit Control Doc, and I want to add a calculator here, I want to go to Menu, 6, Stat Test is 7, and then I want to do a chi-squared goodness of fit, so I'll hit 7 again. We have our observed list, which is our totals. We have our expected list, which we called expected. and we have our degrees of freedom, which is 4. And now we have our chi-squared statistic of 62.5385, our p-value, which was 8.48 times 10 to the negative 13, which is basically 0. So if we wanted to calculate the components for A, I would just need the expected, so the observed value, 89. So this is A's calculation. A would be 89 minus 48.75 squared over our expected value, 48.75. And if I go to my calculator and then I go to vars, I can pull up the component list. And this, for the first value, would be 33.2321. And that's a way of showing the work as well as using the calculator to give you the values. So now we just need to use our logic to understand what is the conclusion that we want to come to from this set of data. We see that our p-value is in essence 0. So the p-value is very small. So we reject the null. There is strong evidence that the most recent grade distribution differs from the historical grade distribution. Significantly more grades of A were given and significantly fewer grades of C were given than expected. And the way that you can tell that is, again, going back to our calculator, we can look at our component list and see that the A's was 33.23, B's was 5, C's was 20.8, D's were 1.7, and E's were 1.1. So very low in the contribution to our chi-squared statistic. But again, we want to look at our standardized values. So to find standardized values, what I'm going to do is use the spreadsheet, and I'm going to say, for this, it's going to be parentheses 89 minus 48.75, and then we're going to divide that through by the square root of 48.75. And in fact, if I type in these values into my spreadsheet, totals would be B1, and then my expected value would be D1. And this is our way of standardizing. And all I can do is if I right click on that, I can say fill, and I can say what cells that I want to fill down to. I can see now I have positive 5.7. That is significantly larger. And I also have, for C's, a negative 4.5. Again, anything over 2 standard deviations is quite unusual. So B's are a little off, but A's have the most, and C's also have the lowest end for looking right versus left. And you can also see that if we look at our distribution, at how off our observed values are with A's, observed values are to C's. So that takes care of an example of goodness of fit. How about we look at a two-way comparison? So a two-way chi-squared test. So part 2 says, as part of a survey, students in a large statistics class were asked whether or not they ate breakfast that morning. The data are summarized in the following table. So we have a 2x2 table, and we're asked, is there evidence that eating breakfast is independent of student sex? So the first thing that we need to do is write our null hypothesis and check our assumptions and conditions before we jump to the calculator. So our null hypothesis, if we're looking to see if breakfast is independent from student sex, our null hypothesis would be whether or not a student eats breakfast is independent of student's sex, with our alternative meaning whether or not a student eats breakfast is not independent. So next, we're going to look at our assumptions and conditions, counted data condition. All of our data are counts of individuals. Again, we have a convenient sample of students, but there's no reason to suspect bias. And this is a convenient sample because a large statistics class was just asked, did you eat breakfast this morning? And we do have to check this because we're trying to generalize this statement. A last bit is our expected counts are greater than 5, so this is met. So now that we've checked our assumptions and conditions, what it's going to ask us is show the calculation for the expected value for females who eat breakfast. So for females who eat breakfast, if we go back up to the table, one way of doing this is we could see how many females there are out of the grand total. So there's 199. Sorry, there's 199 out of 331 females. So we can get that percentage. And then that percentage should also match how many females ate breakfast. So the long work would be if I did 199 divided by 331, and then I multiplied that by how many females said they ate breakfast. And if I type that into the calculator, I get 114.83. But if you're not inclined to do all the work, let's go to the calculator and see how easy a two-way comparison is. So what I want is I want to come up with my data. So I'm going to do a 2x2 because I have 2 rows, 2 columns, sex and yes or no to breakfast. So I have 66, 66, and then 125 and 74. Again, I need to store this. So I'm going to hit Control vars. I'm going to give that a letter A. Once I have stored that in a matrix, now I can go do my chi-squared two-way test. So I'm going to go 6 for statistics, 7 for test, and this time it's 8 for chi-squared two-way test. And all I need to do is select the matrix that I used, and now I'm going to get everything that I need. But specifically, what I want to show you guys is I want to look at the expected matrix and then the component matrix. So I'm going to hit vars, and then I'm going to choose stat expected matrix. And just to save again time, I'm going to hit second store, and we're going to save that in B. Likewise, we hit vars, stat component matrix, and this time I'm going to hit store, and I'm just going to call that C. So now I have both my components, easily recallable, and my expected matrix. So now it says, show the calculation for the component for females who eat breakfast. So again, we're looking at that third cell when we already know that the expected value is 114.831, and our actual value was 125. So what we will do to find this would be 125 minus 114.83 squared all over 114.83. Observed minus expected divided by expected. This will give me one of the components, which we see from our calculator, again, is 0.9000562. And since we've already done the calculation, we can now just give the chi-squared statistic. Now, again, our chi-squared is the sum of each one of these components. So that would be observed minus expected squared over expected. And because we've already done this, and you've shown at least one piece of work, we're not going to write this whole thing out, but our chi-squared statistic, again, if we jump back to our calculator, we go all the way up, would be 5.3391 with a p-value of 0.0208. So now we are asked to make a conclusion. And because the p-value is so small, if we look at our standard alpha level or significance level of 0.05, 0.02 is definitely less than 0.05. So we reject the null hypothesis. There is evidence that eating breakfast is not independent of students' sex. Females were more likely to eat breakfast than males. And if we wanted to actually come up with what is the most significant, again, we're going to go back to our calculator. If we wanted to calculate standardized residuals, we would do A minus B. That gives me my residual value. And then what I want is divided by the square root of the expected value. So in this case, all of these expected values look largely the same. So all I have to do is select this number, hit return, or enter on your calculator. It gives me the value. Then I'm going to get divide, control, square root, and then I'm going to go up to the first matching cell, hit enter, and now I've got negative 1.65 if I put this in a matrix. So we're just going to call this C for standardized residuals. And so we get negative 1.165 for our first cell. Our second, so I'm going to go up here, delete the negative, and this is going to be females. So all you have to do is, once you have that selected and this is gone, just hit enter and you get your value. And so our one below is 0.9489. Again, I'm going to take 1.136. And then our last value, which was now I get negative 1.10. So we can see from our standardized values. Hopefully this was helpful. And we have one more set of notes to go through with part 3 to test for independence, just like we did here.